Hello students, welcome back. Section 3, Inverse Functions. Here in Section 3, we are going to focus upon the derivative computations of inverse functions. Now, before opening up this cell, think of some examples of inverse functions. What kind of inverse functions can you think of? Well, here's an example. The most important class, the logarithmic functions. Among them, the most important is the natural logarithmic function. In that case, here's the derivative formula. The derivative of the natural logarithm is 1 over x, the reciprocal function, or equivalently x to the negative first power. They're the same. Either way is correct. That's the most important. And then, can you think of some further examples of inverse functions? Well, here's some more. Inverse trigonometric functions. Inverse sine, inverse cosine, and inverse tangent. And inverse cosecant, inverse secant, and inverse cotangent functions. All these are examples of inverse functions. Compared to logarithmic, these are far less important. So let's go back to logarithmic functions and get to the bottom of it. And then let's come back to inverse trig functions when we have time. So the most important is this. The derivative formula for the natural logarithmic function is a reciprocal function. Now, how do you prove it? Well, let's not worry about that. We didn't really work on the proofs of those in any of the derivative rules so far, so let's not worry about those. I'm going to cover it in an optional video. For other derivative formulae, let's have a bit of a discussion because they are brief and then they're basically a combination of this rule here and some of those rules we already know that I want to brush up a little bit. I'm going to force you to review. Okay, here's the first. It's basically a composite log function. So how do you take the derivative of a composite function? Of course, it's a chain rule. So take the derivative of a composite function. Then rule number 1 is the derivative of the outside first. Remember, outside first. The outside function is logarithm, so we get 1 over something. You see, 1 over x if the inside had been x, but inside is now u, so this is 1 over u. Rule number 2, nothing changes inside. So u of x just goes in there, goes to denominator, no change. Let me expand the font a little bit with all these fractions. This is going to be helpful. So 1 over u of x. Number 1, number 2. Now number 3. Multiply the derivative of the inside, like a dangling chain. So that's the chain rule here, in the middle part. And then this multiplication applies to the numerator. So in the end, you get u prime of x over u of x. So you can make this one into a formula if you like to and memorize it. But I think it's a bit of an overkilling. You can easily apply the first rule here, which is extremely important, and the chain rule, even more important, and put those together so that you can calculate easily. And that's what you're going to do practically. But don't forget about this form, u prime over u form completely, because that's going to be useful in other aspects too, which we're going to begin discussing from the next video. Not yet, from the next video, when we do the logarithmic differentiation. Okay, so much for the second formula. How about those extensions for arbitrary bases? In that case, we can use the change of base formula. Let me expand the font again. Okay, let's look at the first derivation here. If you use the change of base formula, log of base a of x, which I just highlighted in blue, is natural log of x over natural log of a. Remember that? Up is up, down is down. Up here, x goes upstairs. Down here, the base goes downstairs. So natural log of x over natural log of a. And then we can decompose like this. 1 over natural log of a, which is just a number, so this is just a coefficient. I can always pull it out. And then what's left is 1 over x as before, and after simplification we get 1 over x log of a. But I like this middle form a little bit better. Exactly the same as before, but multiply 1 over log of a. Same thing goes here. We have the coefficient 1 over log of a because of the change of base formula, and that stays after differentiation. Sorry about the typo here. Okay. So in the end, we have all these, but in practice, we are going to do almost everything using only this one and the standard derivative rules, chain rule, product rule, and quotient rule. Okay, ready for an exercise. Okay, alright, here we go. Here's an easy problem. Take the derivative. Oh, this is too easy. Stop the playback and go ahead on your own. What do you get? And then you can go ahead with this one too. Again, this is really easy as well. So take. Okay, alright. All done? I hope so. Okay, let's come back to this. What's the derivative? Outside, 1 over whatever inside, and then by chain rule, multiply the derivative of the inside. In the end, you get u prime of x over u of x, just like this one here. You can use this one directly to go to this. Either way, it works out. But in my opinion, the practical solution is this one here. Chain rule, and then simplification. Okay, how about this? This is going to be a product rule. The derivative of the first function times the second function plus the first function times the derivative of the second function. Derivative of the second function is 1 over x, so it simplifies into just x in the end. X squared times 1 over x. So, a chain rule problem and a product rule problem. Okay, now what if we have an arbitrary base problem, for example, like this one? Let me make up something. Let's see, like this. Base 5, for instance. In that case, what's the derivative? Well, let's simplify this a little bit using the change of base formula. And then divide by natural log of 5. That's a change of base. And then that's 1 over log of 5 times natural log of x squared plus 2x plus 3. And what is this? The same problem as before, same computation as before, except we have coefficient 1 over log of 5, and then the same computation as before. Let's highlight this in red. So that's how you can calculate the arbitrary base case. The only difference, 1 over log of a. That's the only difference. Otherwise the same. Needless to say, the natural logarithms are far more important. Okay, so much for computation of log functions. Now let's spend some time on inverse trigonometric functions. Okay, there are the formulae. And then the derivative formulas for sine and tangent are moderately important. And then the derivative formula for secant is somewhat important. But those cotrig functions, inverse cosine, inverse cosecant, inverse cotangent, those are not very important. And those with negative signs, they're not very important. Okay, we are not going to spend any time proving any of those. At least not just yet. Let's go ahead with some example problems. Okay, alright, here we go. Let's take the derivative. This is just a chain rule, isn't it? So if we take the derivative out of function 1/2 power, subtract from the power, we get that. And then we have to multiply the derivative of the inside. See the structure? Now, inside never changes, so let's just copy and paste it here. Alright, and then here in the bracket, we have to multiply the derivative of the inside. What is the derivative of the inverse tangent function? It's right here, 1/1 plus x squared. Well, that completes the problem. You can simplify if you want to, but if you choose not to, that's fine. Yeah, I did some simplification here. Okay, how about the next problem here? Well, let's see, we have square root here, inverse tangent, and another square root here. So apparently this is another chain rule problem, but two chain rules. So out of function first, 1/2 power, and then subtract 1 from the power, and then multiply the derivative of the inside. How do you like that? Okay, outside done. Now inside never changes. Remember that? Inside never changes. And then we can multiply the derivative of the inside. What's the derivative of the inside? Oh, that's another composite function, so another chain rule. So alright, let's apply the chain rule. Derivative of the outer function, oh, it's arctangent. So okay, here's the formula. And then we have to multiply derivative of the inside. This is square root function, so multiply by power. Subtract 1 from the power. Looks like that's the derivative of inside, and looks like that completes the problem. How about that? All good? No, not really. I just made a mistake. Find out. Where is my mistake? Let's see. Outside, 1/2 comes out and subtract 1 from the power. No problem there. Inside never changes. No problems there. So nothing's wrong here. Something is happening in this bracket. What's wrong? Another hint. Let's see, what's the square root function? 1/2 power, so 1/2 comes out. Subtract 1 from the power, so negative 1/2 power. Nothing's wrong here is either. So something went wrong right here. What's wrong? The answer. The derivative of inverse tangent is 1/1 plus x squared if the inside is x. The derivative of arctangent of x is 1/1 plus x squared, but this time the inside is square root of x. And the chain rule, inside never changes, inside just goes in. So right here, we have to have square root of x, and that thing squared. Or square root of x, excuse me. So this overall, it'll become 1/1 plus x. It's going to become 1/1 plus x. Yeah, 1 plus x. I did this square root expression, but me personally, I like this power form better. Okay, how about the third problem? It's gonna be even worse. We have inverse sine function, and inside we have square root and another function inside. Again, you have to use the chain rule twice. Good luck. I'll leave that to you.